This tutorial video will be reviewing how to read a chemical equation. A chemical equation tells the investigator what happened in the reaction. And you can find all sorts of information in a chemical equation. First of all, you can identify what types of chemicals were mixed together. You can identify any new chemicals that were produced. You can also discover what the ratio has to be of reactants to products. You can tell what state of matter each of the chemicals is, and if in a reaction you're going to produce a gas or a solid. So just a couple of reminders to include in your notes. Remember the term, the gas. Whenever we produce a gas, we are going to put a G next to that chemical, an L for liquid, S for solid, and then very commonly we write the word aqueous. That means it's dissolved in water. Most chemical reactions that we will be working with, we usually dissolve in water because it's the easiest vehicle for chemicals to actually interact with each other. So let's take a look at a chemical reaction. We're going to start a little bit on the easier side of things. Here I have a chemical reaction where if you look at the red lettering, you see that you have a hydrogen and an oxygen producing H2O, also known as water. So just a reminder, everything on the left-hand side of the arrow is called a reactant, because those are the things that are going to react together. Everything on the right side of the arrow is called a product. That is what's produced when the reaction happens. So we've already learned that term subscript that tells us how many of these atoms are bonded together. But one of the things we've never talked about before is the coefficient. And the coefficient tells you how many moles you need to have of each item. So in this scenario, you need to have 2 moles of hydrogen gas with 1 mole of oxygen gas to produce 2 moles of H2O liquid. All right, now what does that actually look like? So as you notice, I rewrote the chemical equation. I have 2 moles of H2. Notice how in the picture above, I have 2 H's bonded together. The reason that I have those bonded together, what gave that away was this little subscript right here. Now that's why I bonded those 2 hydrogens. And then this one tells me that I have 2 of them. All right, and that's why I drew 2 sets. This 2 over here tells me that I need to draw 2 sets of these. 2 atoms of these. So just a reminder, the big coefficient tells you how many sets you need, and the small number tells you how many atoms are bonded together. So here you'll notice, and I'll change color, that for this one, I have the number 2, and for that reason, I drew 2 oxygens bonded together. Now this one's unusual. You'll notice that there is no number here. When you see no number, you always assume 1. So this would be 1 mole of oxygen. When we look at H2O, we see that we have the small subscript 2. That tells us, I'm going to use a different color. That tells us we need to have 2 hydrogens. Do you notice how I have 2 hydrogens drawn? There we go. And then remember, if I don't have a number here, we assume just the number 1, hence why I only have 1 oxygen. Now this coefficient, remember, tells us how many sets or how many groups of this chemical I need. So it tells me I need to have 2 groups, and that's why I wrote those 2. So that's the general gist of what we're going to be working through. So let's try some of our ionic compounds. Now these are all Oh, and just as a reminder, what this reads is 2 moles of hydrogen gas reacts with 1 mole oxygen gas to produce 2 moles of liquid water. All right, so let's practice some using ionic compounds. Now, you don't feel overwhelmed when you see something like this, because in the end, you have worked with these individual ionic compounds all last semester. So let's take this and break it down step by step, okay? The first thing we need to do is we need to actually name these. So let's go ahead and just look at the first one. I have AlNO3, 3. So I look at the periodic table and I recognize that Al is aluminum. And then I notice that in parentheses I have NO3. If I have more than 3 different elements, I know that this is polyatomic. So I look at my polyatomic chart and it tells me that it is nitrate. I do not need to put a Roman numeral by aluminum because remember, it's not a transitional gas, or a transitional metal. All right, now comes the next piece. Looking at my solubility chart, does aluminum nitrate, is it going to be soluble or insoluble? If it is soluble, we are going to use the term aqueous. And aqueous is AQ. If it is insoluble, we are going to write the term, we're going to say that it is solid, because in fact it is, and we're going to use the letter S. So, probably you've already looked at your polyatomic chart to figure out what nitrate is called, and instantly you recognize that you had written down that it's soluble, or you can look at the solubility chart and notice that anything with nitrate is soluble. So remember, soluble means that it's an aqueous solution, it's dissolved in water, and we place AQ right next to it. Now let's work through this next chemical, Na3PO4. Same story, we recognize that this is an ionic compound with polyatomic ions, and so I'm going to call this one sodium phosphate. Sodium phosphate, if I look at it, on the solubility chart is also aqueous. Next, I have another chemical, NaNO3. I look at my periodic table and polyatomic chart and recognize it is called sodium nitrate. And again, I recognize this is also aqueous. Then I have aluminum phosphate. So none of these include transition metals, and for that reason, they are not going to have Roman numerals. Now let's take aluminum phosphate. You're going to notice if you look at your solubility chart that this is insoluble, it is shaded, and for that reason it is a solid. So that was the first task. So now with that, we're able to actually write a written description. So we now take a look at the numbers or the coefficients in front. Remember, if there is no coefficient, we're going to assume 1. And otherwise, if there is a number, then we know that we can actually state that number. So in my written description, I would say 1 mole of aluminum nitrate solution. I'll use the term reacts with 1 mole of sodium phosphate solution to produce 3 moles of sodium nitrate solution and 1 mole of aluminum phosphate, solid. You'll notice that below I have the drawing. Here in my drawing, the red image, you'll see that I have 1 aluminum with 3 nitrates, showing those dots, those electrons, how they transfer. In the next one, I have sodium phosphate. And more importantly, take a look at the green chemicals. You'll notice I have 3 sets of NaO3. Here's one, here's the second set, Here's the third set. I knew to draw 3 sets because of this number 3. And then just 1 set of the aluminum phosphate. So now I want to introduce something of these ratios, okay? Those numbers in the front, those coefficients, tell us the ratio of how much you need. So for example, since I have no number here for aluminum nitrate, I know that that means it's 1 mole. And when I compare aluminum nitrate with NaO3, this one right over here, so if I take a look at this one and a look at this one, I notice that 1 mole of aluminum nitrate will produce 3 moles of NaO3. And so what I can do is I can create conversion factors. All right, we've done conversion factors before. We've done conversion factors where you always have 1 mole over a certain number of grams, but we can use conversion factors for mole-to-mole ratios as well. So simply I would write 1 mole of aluminum nitrate, there we go, is going to always produce 3 moles of sodium nitrate. So I can do that as a conversion factor, or I can flip it over where I say 3 moles of NaNO3 will always produce 1 mole of AlNO3. Okay, so these are considered mole-to-mole conversion factors. I simply place these ratios into a fraction. So let's try the next one. In the next one, I'm going to go ahead and erase these markings here. And we're going to use a different color. For the next one, I'm looking at the ratio of aluminum phosphate to sodium phosphate. So I know that if I have if I produce 1 mole of aluminum phosphate, it means that I reacted or started with 1 mole of sodium phosphate. So let's create that ratio. So that ratio is a 1-to-1 ratio. So I can put 1 mole, and just as a reminder, here's where they are. There we go. So I can say 1 mole of AlPO4 in my conversion factor will react with 1 mole of Na3PO4. Or I can flip it around. They do still tell me the same thing, that if I have 1 mole of NO3PO4 in my reaction, it will produce 1 mole of AlPO4. And you can do this with every relationship in this chemical equation. So let's do another set. And like I said, you can compare any of these two to get this answer. Let's give it a try and go for green. So for the next one, it is looking at the relationship between NaO3 and AlPO4. Okay, so let me see if I can get my marker here. There we go. So in this relationship, we notice that if 3 moles of NO3 are produced, 1 mole of AlPO4 was also produced. Remember, these are the products on the right-hand side of our equation, and these are the ones that are produced. So let's write down our conversion factors. That means that for 3 moles of NO3 that are produced, 1 mole of AlPO4 is also produced, or 1 mole of AlPO4. If you produce 1 mole of AlPO4, we also will produce 3 moles of NaO3. All right, let's try one more set where we're going to now look at it in a different way. In this scenario, you're actually given the description, and now you need to write the chemical equation. So you're told that you have 1 mole of lead-2 nitrate reacting with 2 moles of lithium iodide to produce 1 mole of lead-2 iodide and 2 moles of lithium nitrate. So There's our written description, repeated again. So now what we need to do is we need to write the equation. Before we write the equation, we need to make certain we know what these chemical formulas are. So let's start with each one individually. Let's do a lead 2 nitrate. So for lead 2 nitrate, I have lead, which is Pb. I know that that Roman numeral 2 tells me I have 2 valence electrons. Nitrate, when I use that, I know it has an 8 ending, so it's going to be on the polyatomic chart. And nitrate is going to have a -1 charge, which tells us it has 7 valence electrons. All right, so that means that this lead can get rid of one of its electrons. The nitrate gets 8 of a full valence shell, but keep in mind that this this lead still wants to get rid of one more electron. And so we have to draw another nitrate so that the lead can get rid of its last electron. So that means in our equation that we're going to count this out. We have 1 lead and 2 nitrates, like we've been doing this semester all along. I'm told there is 1 mole of this, so I leave this, this area blank. The next piece is I need to look at its solubility. And if you look at your solubility chart, you'll see that nitrates are always aqueous. All right, so now we need to do the next chemical. So for the next chemical, I'm told I have 2 moles of lithium iodide. So let's go ahead and put the 2 in front because we know that we have 2 moles of it. That's the coefficient. Notice this does not have an 8 ending. It has an IDE ending, IDE, which means that I need to look at my periodic table for this one. So lithium, I know, has 1 valence electron, and iodide has 7. Oh, I notice this is going to be an easy one. It is simply 1 lithium and 1 iodide that will get us to have the full valence shell. All right, so I simply write 2Li with a capital I. Remember that 2 comes from this 2 right here. Now, once I see that word produce, I know that that means I'm going to draw an arrow. And at that point, we've got 1 mole of, let me use a different color for this one. Clean that up. So we have 1 mole of lead 2 nitrate. Okay, so let's go ahead and do this. Now keep in mind, for this one here, I want to draw 2 of these. So let me take 1 step back here. Why do I draw 2 of them? Because of that coefficient that tells me I have 2 of them. There we go. Okay, so let's do the next one, which is lead 2 iodide. So I have lead, which has 2 valence electrons. Remember that IDE ending tells me that it's just plain iodine. And so that is just an I. Remember, looking at the periodic table, it has 7 valence electrons. Well, that means that the lead can get rid of one of its electrons, but it still wants to get rid of the other one. Okay, and that tells us, oh, and I'm sorry, I wanted to mention also, well, let me write down the chemical equation, or the chemical formula. So that tells me that it's PbI2. So one of the things we need to include is whether or not it's going to be soluble or insoluble. When I look at my solubility chart, this tells me that it is a solid. And I just realized that I didn't do that for my lithium iodide. Lithium is an alkali metal, so I know that that is going to be aqueous. I'm told I just have 1 mole of lead 2 iodine, and so for that reason, I'm going to just simply leave it blank. So now let's add the last piece. I have 2 moles of lithium nitrate. So again, I'll draw that out. Lithium has 1 valence electron. Nitrate has 7. Okay, and it looks like I just need 1 lithium for 1 nitrate, but don't forget this 2. This tells me that I have 2 LiNO3, right? So I'm going to have to draw 2 sets of these. There we are. And I look at my solubility chart, or I can simply look at my periodic table and my polyatomic chart, and it will tell me that those are aqueous. All right, so you will notice that writing the equation is always a lot more work than actually being given the equation and writing the description, because you have to remember to do the drawings so you can get an accurate chemical formula. So now let's take a look at these ratios, okay? So for these ratios, I'm going to, for the first one, look at the relationship between lithium iodide and lead iodide, all right? And it tells me this chemical equation for every 2 moles of lithium iodide that I use will produce 1 mole of lead iodide. So what would the conversion factor look like? So I'm going to write 2 mole LiI over 1 mole PbI2, or I can do the reverse. I can write, oops, let's make that look like 1 mole of PbI2 over 2 moles of LiL. So let's try the next one. Okay, for the next relationship, we are going to take a look at the relationship of lead nitrate with lead iodide, and I see that if I have 1 mole, remember if there's no number in the front, it would be number 1. If I have 1 mole of lead nitrate, it will produce 1 mole of lead iodide. So this is a 1-to-1 ratio. 1 mole PbNO3 for every, if we use 1 mole of PbNO3, 1 mole of PbI2 is produced. Or I can flip it. Either one is fine. Okay, and let's do the last one. Let's look at the relationship of those two. For that one, I'm looking at the relationship of lithium iodide with lead nitrate. If I use 2 moles of lithium iodide, I also must use 1 mole of PbNO3. Okay, those are the ratios of what you need to put into the reaction. So let's use those as conversion factors. 1 mole PbNO3. If you have 1 mole of PbNO3, you need to have 2 moles of LiI, or if you have 2 moles of LiI, it requires 1 mole of PbNO32. Okay?